first. For example, I'll highly recommend, if you feel like those problems too hard, I will highly recommend you to take a prerequisite course called Mathematical Foundations for Data Science, taught by my colleague Jeff Phillips. I think the course number is 3190, but you can just search the names. It's called Mathematical Foundations for Data Science. I would believe that, I mean, if you are not sure about your background for machine learning, if you take that class, I won't be worried about my background anymore. Okay, so today we're gonna first give a quick review of some basic knowledge that will be used in the following lectures. However, due to the schedule, this is not a comprehensive or in-depth review. Actually, we assume all those concepts, definitions you have heard before. At least you were familiar with that, and if you feel a little bit strange right now, you can, if it is okay for you to search on Google, Wikipedia, or find some online course material that help you refresh your mind and get back, that's totally fine. It's not necessary for you to memorize all the definitions. But if it is completely strange, then that is problematic. Okay, so we'll first give a quick review of those basic knowledge, and then we'll start talking about real machine learning topic. We'll first introduce the general setting for supervised learning, the most important framework we're going to discuss or concentrate on throughout this semester, and then we'll introduce the representation of our first machine learning models called decision trees. Okay, so first basic knowledge review, right? We're gonna briefly discuss some key concepts or definitions in probability or statistics, right? So first, we're going to talk about random events and the definition of their probabilities, right? So what are random events? It's just record or describe the results of your random experiments. And random experiments has a very broad sense, meaning that you can view whatever things you're doing with some randomness in nature. For example, suppose right now you're doing some corn tossing, right? You just toss a corn and want to say if you have heads or tails on the floor, right? This is just random experiments. And my specific random experiment is just to toss a corn for 5 times and then look at the heads and tails sequences, right? So I can use a set to represent the event, right? For example, event A indicates my results of my event is that, okay, the first 3 are heads and the remaining 2 are tails. And event B, which is represented by another set, means that, okay, your result sequence is tail, head, and tail. Right? So in a more general sense, I mean, people always use sets to represent random events, where each element in a set is a atomic outcome of your random experiments. Like, for example, you toss a coin for many times, but each time you know the outcome is either head or tail, right? This is the atomic outcome. And given the event A, given any event, right, represented by sets, we're going to assign a probability which measures the chance that event happens, right? So we assign probability A for the event A, so we denote it by P of A. Probability B denoted by P of B, right? So you can say it's a interesting definition. The probability essentially is a function that map sets to a chance, which is a real number between 0 and 1. So it's a mapping between sets and values between 0 and 1. So such definition in general is called measure, a probability measure. If you have taken some mathematical course, in depth, people will tell you that measure, what is definition of measures? Measures actually are functions between sets and mappings between sets and real numbers. And probability are a special type of measure where your output or the function value are just between 0 and 1. But if you don't restrict that, it can be any measure, like counting measure, whatever. Okay. So because we define the events with sets, right? We know that there are many operations between the sets, right? So we can use set operations to create new events. Suppose we're given A and B, right? We give A and B. We can create a third event. That is, both A and B happen. Okay? What kind of set operation will be used? It's just intersection. Intersection of A and B is another event, meaning that the event A and B both happen. And another commonly used set operation is a union, right? So if we represent A union B, which is the third event C, what does C mean? C means A or B happens. So be aware of the difference between both A and B happen and A or B happens. Right? A or B happens actually, you can view it as two cases. First case is that both A and B happen. Second case is either A happen or B happens, right? So conceptually, we know that the probability of A union B is no less than the probability of A intersection with B. So this can be more precisely characterized by this formula, right? Which I believe everyone has seen in your textbook before. The probability of A union B is calculated by the probability of A plus probability of B subtracted by the probability intersection of B. So this has a very intuitive explanation from by the Venn diagram. If you just draw two, maybe I can use the ball here. No.
There's a chalkboard in. Look down in the thing. There's a chalkboard in there. It's forward and then down.
Forward and down?
Yeah.
Oh, this one. Oh, okay. Thank you. So how to understand this equation, right? So we can use Venn diagram. Like, we can draw a big circle, represents the even A, right? And the area of this circle is the probability of A. Well, we can also draw another circle, represent the even B, right? Of course, the area of this circle indicates the probability of B, right? So how can we calculate the probability of A union B? Note, this is third event. It's another event. It's different from A and different from B, right? So essentially to calculate the area of A union B, right? So how to calculate that? We can simply add the area of A, which is P of A, area of B, but we're gonna subtract it by A intersection with B. Why? Because this part, if we add A, we add as B, we actually add this overlapping part for twice, right? So we're gonna minus this overlapping part to ensure they are not double counted. Okay. So this is really how we understand this infinity. But in general, I mean, there are more sophisticated formula talking about how do you calculate the joint probability for n events, right? So suppose you have a n, how do you calculate the union of A1, A2 to AN, which we're not going to discuss in detail in this class, but if you're interested, just open your textbook or search on Wikipedia, they have a formula, they have a long formula, but the idea is it simply just adds up all the probabilities of single events and subtracted by the combinations, and added the triple combinations and subtracted by the four combinations, and until so on and so on, right? So this is basics about the definition of events and how we assign probabilities, how we calculate their probability of their set operations, right? So, but in most probability or statistical applications, we're not directly operating on sets. Why? It is not convenient, right? So everyone is familiar with the real system, continuous values. So you can take integral, you can take derivative, all kinds of stuff. So you have a lot of richer mathematical tools and analytical tools, right? So people therefore define the so-called random variables, right? So we use numbers to represent the sample outcomes, namely heads or tails. Right? And then we call those numbers as random variables. Then we represent events by random variables following some regions. Right? And well, this is a very, I can say, just very intuitive explanation of random variables. If you get a chance to look at the measure theory-based probabilities, random variable is essentially mapping from the sample space, the outcomes to the real value space. But anyway, we can roughly understand random variables in that way. So to take an example, now suppose our experiment is due to toss a coin, right? And for this particular coin, the outcome, we introduce random variable x. X is binary. X takes 1, meaning that your coin has heads up, right? X equals 0, meaning that your coin has tails up, right? So now we represent outcomes of your experiment by a random variable. Now suppose we toss a coin for 5 times, then we'll represent outcome for each experiment by x1, x2 to x5. Right? Now we can look into a variety of events in terms of values of x1 to x5. For example, I want to describe a particular event or define an event that out of these 5 toss coins, we have less than 3 heads. How can we represent that event? We can simply add up the summation of x1 to x5 and use this inequality. We use this inequality to denote you have an event that you have less than 3 heads out of 5 tosses, right? And then to calculate the probability of event, it becomes calculating the probability of this inequality holds. Probability of x1 sum to x5 less than 3. And you can define all kinds of events you like according to the values of x1 to x5. Okay. So now, given the definition of events and random variables, we can define the joint probability over multiple events or multiple random variables. So there is a key decomposition where everyone should know is that how we decompose the joint probability of a set of events or joint probability of a set of variables, right? But they have exactly the same form. So suppose we have 2 events, A and B. So the joint probability of A and B basically means the probability of A and B both happens. Right? So it's a intersection of A and B. Right? So don't be confused. And this joint probability can be decomposed as the probability of A, which is often referred to as marginal probability of A, times the conditional probability P of B given. Basically means the probability that B happens given A happens. And symmetrically, this joint probability can be written as or decomposed as the marginal probability of B happens times the conditional probability of A happens given that B happens. Right? And of course, you can write a long chain for many events. Like you have A1, A2, A2, A1, A2, A3 to AN. You can write it down as a multiplication of a set of conditional probabilities, which I refer you to your textbooks or Wikipedia or whatever. And then similarly, if we switch to random variables, you have two random variables, P of X and Y. The joint probability of X and Y can be decomposed of P of X, which is usually referred to as marginal probability, multiplied with the conditional probability of Y given X. Symmetrically, we have this also equal to P of Y, namely the marginal probability of Y, multiplied with the conditional probability of X given Y. Okay. Someone asks, okay, what about X, Y are discrete? What about X, Y are continuous? It doesn't matter. They have the same form. And for the continuous random variables, this is usually referred to as probability densities. So a very important concept when we deal with multiple random variables or events is their independence. Right? We want to know that if those two events or two random variables, they're independent to each other. Right? But what's the definition of independence? So suppose we have two events A and B. A and B are independent to each other if and only if their joint probability is equal to the product of their marginal probabilities. That's it. That's the key definition. Okay. So similarly, if we say two random variables are independent to each other, it basically says their joint probability is equal to the product of their respective marginal probabilities. And ask me, you can ask any questions.
So you're saying that if the product of PA and PB is equal to that, then they're independent of each other?
Yes, that's the definition. So that means if you want to show that any two events are independent of each other, you need to show this. Or you want to justify two random variables are independent, you need to show that okay, their joint probability is equal to P of X multiplied with P of Y. Okay. Any other questions?
Can you show joint probability like the Venn diagram that you were just drawing for the A union B?
Oh, it's just so basically it says this part area is equal to this area multiplied with this area.
Oh, okay.
Yeah, that's it. But usually people won't use one diagram to show the product relationship between the events. We're just talking about the addition of events, the union of events, intersection of events, their relationship. Any other question?
So we can't get the intuition behind it. So and we can accept it just as a definition.
What?
So I mean, like, what is the intuition behind it? I mean, so we consider like A and B as independent if they are like their probability of A multiplied probability of B is equal to
Yeah. So the intuition is if A and B are independent of each other, right? Like you and me. I mean, it's not. It might be an inappropriate metaphor, but it's just like that. For example, you toss a coin, I toss a coin. You do gambling, I do gambling, and you got 0.6 chance to win today. I got 0.6 chance to win today. So what do you think the probability of we both win today? It's 0.6 multiplied with 0.6, right? But if we have some high dependence to each other, that won't be 0.6 squared, right? Okay. So now another way to view independence is by contrasting the two definitions. So the decomposition of the joint probability. This is in general. No matter A and B are independent of each other, or X, Y are independent of each other. Right? But if they're independent, their decomposition will follow this way. If we contrast the equations on the top and on the bottom, what we can observe, actually, independence can be represented in that way, meaning that you can see that if A and B are independent, meaning that joint probability of A and B equals P of A times P of B, right? In general, joint probability of A and B equals to P of A multiplied with the conditional probability of B given A. So if they're equal to each other, it basically means the marginal probability of B is the same as the conditional probability of B given A. So you can see that actually reflects, meaning that the happening or the occurrence of B has nothing to do with the even A, right? Because the conditional probability of B given A is the same as the marginal probability of B. So similar analogy can be made for the random variables. And we can extend the independency, the concept of independency to conditional independency. So basic conditional independency saying that, okay, conditional on a third even C, A and B are independent to each other. What does it mean? Just the extension, right? So if we say A and B are independent given or conditional on C, it basically says the joint probability of A and B given C is the product of the probability of A given C times probability of B given C. And similarly, if we see two random variables x, y are conditionally independent given a third random variable z, it says it means that, okay, this joint probability given z is equal to the probability of x given z times probability of y given z. These are only definitions, so don't ask me why. Don't ask why it is defined like that. Yeah, it's defined like that. Okay. So given random variables, because much of our efforts in probability and statistics will be focused on random variables. Right? Given any random variable, we're always interested in several statistics associated with that random variable. The first one is expectation. Okay? So you can imagine a random variable, because of randomness, it has a chance to take that value, to take that value, to take that value. The chance is determined by the probability. Or more rigorously speaking, probability density, right? But we want to know that what is on average the value of that random variable. Right? That's the definition of the expectation. Right? So the expectation is defined as the average value of the random variable, and this value is actually weighted average y because it's weighted by the probability or probability density. So generally, expectation of x is an integral of x multiplied with probability density. That's it. Someone may ask, okay, what if x is a discrete? Doesn't matter because discrete variable integral becomes summation, right? Summation over finite number of possible values x and k. So we have we essentially have a uniform definition, right? And we can extend the definition of expectation for random variable to a function of random variable. So any function of random variable is also a random variable. So when we calculate the expectation of some function g of x, how can we do that? We just replace x by g of x in this integral. That's it. Okay. And a second statistics we are very interested in arbitrary random variable is variance. So what does variance mean? Intuitively speaking, it just means how far away x on average is distant or jump away from its mean or expectation. Right? So you can imagine that, suppose this is a random variable, right? This is its mean. I mean, on average, the value of x is here, right? But x is a random variable. You can see maybe one sample it takes here, one sample it takes here. So it has a chances to jump around the mean, right? The variance is just a measurement, indicates on average how far away the x takes the value from the difference between the x value from its mean. That's the variance. So the definition of variance is based on expectation. So it is expectation of x squared subtracted by square of expectation. You can show that it is always non-negative. And another definition, I think everyone should know, which I omit here. So I think it's worth writing out. So another definition is expectation of x subtracted by its mean and t squared. Right? So I think it's basic math to show that this is expectation squared subtracted by square of expectations. And someone asks, what if x is vector? Right? Well, when x is vector is no longer scalar, just use variance of each individual element in x is not sufficient, right? So in that case, we extend variance to the so-called covariance matrix. Right? Covariance matrix, suppose x is n-dimensional, then the covariance matrix will be n by n matrix. Right? The definition is very similar to here, right? But remember, this is a matrix, right? This is the expectation of x transpose. So x is an n-dimensional vector, x transpose is the auto product, which is n by n matrix. Then subtracted by expectation of x times expectation x transpose. Right? And we can show that this is always positive sign definite. And similarly, we can define conditional expectation and conditional variance. So what is conditional expectation? Any clue? How we extend this to get a conditional expectation? Don't be shy. Yeah, you replace P of x by the conditional probability P of x given y. That's it. And the conditional variance is the same thing. The only change you made is that you're gonna calculate the conditional x squared given y, subtract the conditional x given y squared. That's it. So this is actually almost the same definition, except that you're going to replace the density of probability here by the conditional probability. That's it. Okay, those are about some fundamental concepts in probability and statistics that everybody should know. And don't tell me you'll feel very strange about this. That's not a good sign. So now let us talk about convex functions. Convex functions are a family of functions which are very widely used in machine learning. Right? So so first, the domain of the convex functions are defined on a so-called convex region. Right? Convex functions define a convex region, mapping inputs from convex region to some real value. Right? So what is convex region? So convex region is a special type of sets where geometrically speaking, the shape of the site is kind of outward. It cannot have an inward. Why? Because we require that for a convex region, if you pick any 2 points inside this region, and you can connect the 2 points by a segment, right? By a line and a segment. And we require every point on this segment to stay inside this region. That's the definition of convex region. And this is obviously a convex region. You can draw different lines and to test it. But here we want to give a counterexample. So this is not a convex region. Globally, it is kind of inward because you have one part going inward, right? And from the definition, if you pick up x and y here, and if you draw a line connecting x and y, you can see that the red parts, all the points on this red section, they are outside of the convex region. They're outside the region, so it's not convex region. Does it make sense?
But x and y are convex regions?
No.
Like where they are?
X and y are just 2 points in this set. the convex region requires that, okay, if you connect any 2 points in this region, all the points on that section connecting the 2 points must stay inside the region as well. So you can see that if I pick up x and y here, if I draw a line between them, we can see that the right part stay outside. It's no longer inside. So this blue shape like kidney is not a convex region. Huh? Does it make sense? Okay. So now let us talk about the definition of a convex function. So the domain of the convex function is a convex region, and then it maps to a real value. We're now going to talk about complex functions. So for a convex function, it must satisfy an inequality, which is usually referred to as convex inequality. So what does it mean, right? Let me first read through the formal definition and give some visual illustration. For any 2 points inside this domain, and any proportion t, which is between 0 and 1, if we combine x1, and x2 in terms of t, this is usually referred to as a convex combination. If our function evaluated at this convex combination of x1 and x2 in terms of t is always less than or equal to the convex combination of the function values at x1 and x2. This is called convex function. So what does it mean, right? It seems a kind of tedious definition, right? So here's the visual explanation, which give a much better intuition about this definition. So f of x here is a typical convex function. Let's see how this function satisfies this convex inequality. So the whole x-axis is the domain of this function, right? So we can pick up arbitrary 2 points, x1, x2. Okay. So, and we pick up t, which is between 0 and 1. And then the convex combination of x1 and x2, according to t, is here. Is in the middle, right? t x1 plus 1 minus t x2, right? So we can look at the left-hand side. When we evaluate the function at the convex combination of the inputs, it's here. Right? And then let us look at the right-hand side. Right? The right-hand side is convex combination of the function values at x1 and x2. So here is function values at x1. Here is function values at x2. Right? And then we do the convex combination of these 2 function values. It is here. Okay. So you can see that the convex combination of the function values is bigger than the function value at the convex combination of the inputs. That's how we usually explain the meaning of this convex inequality. So basically, it requires that for a convex function, for arbitrary 2 inputs, this inequality holds. So here are a few examples of commonly used convex functions. Right? If your input is just a scalar, single variable, like exponential function is a typical convex function. Negative logarithm of x is convex function. And for a vector function, meaning that your input is a vector, it's not just a simple scalar, you can show that this linear function, sometimes people refer it to as Eigen function is a convex, and quadratic function is convex. So given an arbitrary function, how do you determine or how do you test if this function is convex or not, right? Of course, we can use the definition, right? You can just, if we can show that for arbitrary 2 inputs in the domain, this convex, an arbitrary t, right? This convex inequality always holds. Of course, we can do that, right? But that is not always convenient, right? So here are 2 often used testing conditions or sufficient conditions, right? First, if this function is differentiable, then if we can show that for arbitrary x and y, this inequality always holds, then this is convex. So what does this mean?
that small triangle, that's a gradient vector,
Yes.
right?
This is a tangent line. Okay. This is tangent line. So basically, the meaning of this being equation, right? Let me get it down. Right? It's basically say that if this is a convex function, right? If this is a convex function, the right hand side just represent the tangent line passing through this input. Sorry. The right hand side. And fx is arbitrary, right? That basically means, okay, the whole function curve must stay above this tangent line. That's the geometry meaning, but it's we won't go through deeper about this meaning, just to give you a hint. And if this function has even better property, meaning that it's twice differentiable, if you can show that it's Hessian matrix. Remember, it's our last problem in homework 0, right? You can show that this Hessian matrix is positive semi-definite, then this is convex, right? But regarding how you show this, how do you correspond this to the definition of convex? It's out of the scope of this lecture. Just to give you a sense. Okay, so associated with convex functions are famous inequalities called Jensen's inequality. So if you got a chance to know more about probability inference, like K techniques, a very widely used techniques called variational inference. The definition or whole technology of variational inference is derived based on the Jensen's inequality. So what does Jensen's inequality tell us? If f is convex and x is random variable, then the function value at the expectation of x is less than or equal to the expectation of f of x. So remember, x is random variable, right? So f of x is random variable as well. So it is reasonable that we have expectation over f of x. And this can be easily extended to functional random variables, right? If you make a transformation x, you get another random variable g of x, and this inequality also holds. Okay, the last piece of topic I want to briefly mention is the matrix derivatives. And I think thanks to the numerical libraries developed so far, most of us won't need to manually derive the matrix derivatives, but I think still necessary for you to know the basics. So what is matrix derivatives? Basically means that, okay, if your function, if your objective function, if your loss function is a function of a vector, or even function of matrix, right? And how do you calculate the gradient of your objective function with respect to a vector input or matrix input? That's about matrix derivatives. And anyone who has heard of or have applied Jacobian matrix should be fine with this topic, so don't be scared. There's nothing to be scared of. So the basic idea is that we have a set of basic facts which are summarized by mathematicians. So when you calculate the derivative of any loss or function with respect to vector and derivatives, you can apply all kind of rules to reduce them to the combination of those basic facts, and then just apply it. And our team has shared several resources about how to look up the existing facts about matrix derivatives and vector derivatives, and like matrix cookbook, and very good tutorial written by Tom Inca, matrix and vector derivatives. I highly suggest everyone to take a look. But the basic idea is like that. We know that the derivative of a constant matrix is 0. This is a 0 matrix. And the derivative of a constant scalar multiplying with a variable matrix variable x is alpha times the derivative of x. And derivative of x plus 1 equals derivative of x plus derivative of y. You see it's almost the same as the scalar case. Okay, I think that's pretty much all we're going to talk about this basic knowledge. Right? So again, if it is good, if you feel okay, I just kind of like some kind of concepts are not that familiar, but I was familiar, that's totally fine. Don't worry. But if you feel, okay, I never heard of those concepts, or those sounds terrible, that is problematic. That's problematic. And we assume that you all at least heard of those concepts. Because later we'll discuss, especially like how do you calculate derivatives, how do you apply the chain rules. Everyone need to implement your back propagation with deep neural nets. If you don't understand chain rules, never think about that. If you understand chain rules, you'll see, okay, back propagation is simply application of chain rules, a very smart application of chain rules. Okay? All right, now we're going to talk about actual things about machine learning. And okay, we're going to first introduce the general setting of supervised learning, the whole umbrella, under which we're going to discuss a series of quite a few supervised learning models. They have different design principles, ideas, algorithms, steps, and so on. But they follow the same kind of high-level principle and protocol. And then we're going to introduce decision tree representation, but it depends on the progress today. So what is supervised learning? Before we conduct any supervised learning, we need to be clear what are our instances and what are labels. Right? I want to use this particular example, namely our task is to automatically tag news articles, right, to illustrate the concepts. Right? So an instance for this particular task, obviously, is a particular news article. Right? And the label is actually the label I want to attach to this. I want to tag this document. Like this particular article, I may classify as sports. Right? Another article I may classify as politics or entertainment and so on. Right? So basically, we can collect, or we can imagine we have collected all possible instances, meaning all possible news articles to be tagged. Right? And the labels consist of all possible labels we can use to tag, like sports, like business, politics, entertainment, and so on. You might come up 20 categories or 20 tags. So here we can abstract the concept of instance to instance space and labels to label space. So instance space are all possible news articles, and label space are possible labels. So in general, whenever we are doing some machine learning tasks, right, we always need to properly define a so-called instance space, which consists of the set of examples that need to be classified, that need to be predicted. Right? And then we need to define the label space, which means all possible labels, those instances can be classified too. Right? For example, in addition to the articles, the instance space can be a set of all possible names if you are playing batch games, if you are still have an impression about our batch game last week. And documents, if you're doing document classification, if you want to do the image classification, to detect if your image contains the dog or not, right? So those are instances, or basically, roughly speaking, you can view it as the inputs, all possible inputs to a machine learning model. Right? And then you need to define the label space, right? For example, if your task is to do the spam filtering, right? Then your label is spam or not spam, right? If you're doing binary classification, your label could be positive sign or negative sign. So, given the instance space and the label space, a fundamental assumption in supervised learning is that we believe there is some mapping between these two spaces, which is called target function, or on the ground truth target function, which gives any instance in the instance space a label in the label space. Of course, if we can derive this function, we do not need to do any machine learning. So, but usually this function is highly complicated. We don't know that. We never know, and in most cases we even do not have some analytical form. So the goal of machine learning is to find out this target function based on data or examples. Okay. So more specifically, learning is essentially a search procedure over functions. Right? You always assume, okay, there's a family of functions which might contain this target function, or might contain some function which is as close enough as possible to the target function, and you design some searching procedure to identify this best function. So the learning algorithm always sees example of the function in action. Again, that's what I want to emphasize. Because if you know the form of this ground truth or target function, then there's no need to do any machine learning. But how can we conduct supervised learning? Right? The examples of the functions must be in the form of pairs of the instance and their labels. So we need to prepare a collection of labeled training data. X1, f of x1. F of x1 is essentially the label of this instance. X2, f of x2, the label of this instance x2. And suppose you have collected n examples. You feed them to our learning algorithm. And learning algorithm will search over the functions and guided by this training data to find something. And we denote this learn function by G, which is also a mapping from instance space to the label space. Then we believe that our learn function G is either is the target function or close enough to the target function. That's the whole setting or the framework of supervised learning. So the question is, can you think of other protocols? What if I do not provide the labels? Right? I will give you x1, x2, x3, and the instances from instance space. I do not give you any labels. And someone asks, if I feed such kind of data, which we usually refer to as unlabeled training data, can we still learn something? And the answer is yes. And this learning is called unsupervised learning. So you can see the unsupervised learning. The difference between the unsupervised learning and supervised learning is that in the data preparation, right? Supervised learning requires you to give the labels for each training instance, right? But unsupervised learning, you don't need to give the labels. And semi-supervised learning is actually a hybrid of supervised learning and unsupervised learning. Namely, part of the training examples inputs will assign labels, give the labels, and part of do not have. And can we still learn something? Learn this function G maps from instance space to the label space. So, but again, although the training or the learning protocol can vary according to the data format, the most important topic is still supervised learning, because once you know techniques in this framework, it can be easily extended to unsupervised learning, semi-supervised learning. They're all in a kind of similar fashion. Okay. Now I'm talking about the whole protocol to conduct supervised learning. Suppose we're done, right? We have obtained a learn function G. Okay. The next question is that how can we evaluate the performance of the learn function G, right? Can we just compare G and F? The answer is no, right? Because I don't know the exact form of F, right? If I know exact form of f, why should I do machine learning, right? I'm already succeeded, right? So I don't know the function, the ground truth target function f. Right? Then how do I evaluate if G is accurate or good? Any thought?
Test it on something you didn't use to train it on?
Okay, test it again.
Test it on something you didn't use to train it on?
Yes, exactly, right? Anyone who wants to, you want to supplement? The same idea? Okay, great. Yeah, you're right. Because we don't know the exact form of f. I don't have a mechanism to access the form of f. It's not possible to directly compare the form of G and the form of f. Right? Then how can we evaluate? Similar to training. I'm gonna sample a bunch of instances from the instance space and then look at the label given by the ground truth, a label given by our learn function, and to see if they match. Right? If in most cases the label given by G is the same as the label given by f, then that indicates okay, you have learned a very good function. And otherwise means that okay, the performance, you still have the room to improve your learning model algorithm. So now I want to ask, can we use test examples during training? Any thought?
I would think no, since you're trying to see if it can adapt to new situations. So.
Yes, exactly. And any supplement?
Like you would assume it would always get those right because they use them to train stuff.
Yeah.
I guess it would depend on what state you call finalized, or if your algorithm or learn function is always learning, or if it has an end goal where you want it to stop. Because if it's always learning, it's always training.
Yeah, it's always training. But right now we're talking about the stage, the task stage. I mean, it's our learning has ended. That's what you said. It's actually so-called final stage. Right? So basically, one thing I think this point is very, philosophically is right, because learning is essentially a way to adapt to the new things, right? You can test such kind of adaptability with the case you haven't seen before, right? And practically speaking, many machine learning models are so powerful they can memorize the training examples. That means if you use test example during training, and during the test again, it just report exactly the same label. That means no matter your actual performance is, you might have a 100% accuracy, which is obviously not right. So this is called cheating. So that's a very, very important practical principle, and even many experienced machine learning engineers or researchers make such kind of mistakes. So in the future, I mean, when you do a project, when you do a homework assignments, when you find your model gives 99% accuracy, 100% accuracy, don't celebrate and check if you happen to mix training and test examples. That's very important. Okay, let me summarize the general setting for supervised learning, like just integrate all the information we have discussed so far. So basically, we assume the data, or training data, are given in the form pairs of the instance and the labels. And of course, the label are given by some ground truth on the line, ground truth function, right? And this is usually unknown, and there's no way to know its exact form. Right? And the input x is really represented by feature vectors. So the space where those feature vectors stay is called feature space. For example, in some applications you might use a binary vector to represent your instance. Some applications you just use numerical vector, n-dimensional numeric vector to represent that. So this relates to some pre-processing step. So basically, we'll collect the raw data. It's not always feasible to directly feed them to your training model algorithm. You always need to do some pre-processing. Like you convert the raw data into some feature vector and to represent their instance X. Why? Because in many situations, the computers cannot recognize the meaning of that. Like you cannot feed the newspaper to a computer. Like, it doesn't recognize letters. You have to convert them into some numerical representations. Like for raw images, you give it a very high dimensional RGB values. It's really not that way for computers to recognize. You have to run some feature extraction procedure to give some informative or easy to deal with data format for the computer program to process. So there's often a pre-processing step to that, and it's quite critical in practice, and which you'll see in your homework assignments and your project. And then our goal in supervised learning is to find a good approximation for this underlying ground truth function f. Right? So although in some ideal case we might want to see that if we can exactly recover f, right? In practice, it is nearly always infeasible. Our best expectation is that we want to find approximation to f to be as close to f as possible. And finally, the labels actually determine the kind of problem, a particular type of problem. For example, if you are doing binary classification, then your label space only consists of 2 labels, right? If your label space consists of like k discrete labels, then that means you are doing multi-class classification. If your labels happen to be continuous, like stock price, like temperature, like participation, and contamination, whatever, right? Then your label space is continuous, means that you are doing regression. Okay, any questions so far about this general setting? I believe this is pretty straightforward. Okay, great. I just want everyone to know that what is the ingredients to conduct supervised learning. And when we talk about all kinds of algorithms, we assume that you have all those things ready. Okay? Okay. Whenever we want to conduct supervised learning, we need to ask ourselves a few questions. Like, what is our instance space? Like, how do you prepare training instances? How do you conduct pre-processing step? What is our label space, right? What kind of tasks we're doing? If you want to do the regression, it means that you want to predict continuous labels. If you want to do the binary classification, then your label space is 2 items, right? 2 labels, and so on. And the third question is, what is our hypothesis space? Hypothesis space meaning that what kind of functions you believe will contain the best approximation to the ground truth f. Right? So you need to carefully choose the hypothesis space. Actually, in the later lectures, we'll discuss some kind of trade-off. If you choose hypothesis to be very large, then you will take the risk to overfit the trained data. If you choose the hypothesis to be too simple, means that the candidate function, the set of candidate functions is very small, then you have the risk of underfit data. So it's not like the larger, the richer hypothesis space, you will get more successful. It's not like that. It's kind of trade-off. And what is our learning algorithm, right? This is referred to the algorithm design step. You'll see that in several cases, you need to find the trade-off between efficiency and effect. Like in decision tree, you find that you cannot brutally search all tree structures. We have to use some greedy structures. Otherwise, it won't be practical. And what is our loss function or evaluation metric? So, given this task, right? Given this particular task, how can we evaluate if our machine learning model works well or not? Right? And you see that many learning procedure essentially to minimize the so-called loss function. Okay, here are taxonomies which we have briefly introduced when we talk about the course schedule. But basically, supervised learning, unsupervised, and semi-supervised learning, and our focus throughout this semester will be the supervised learning. Right? And we'll start with the so-called decision trees. Okay. So what are decision trees? And we're going to first introduce what the representation decision trees gives. You can see that it's essentially a hierarchical representation of the data. And then we'll talk about the algorithm steps of learning decision trees. How to create a decision tree from data. We'll talk about this classical algorithm called ID3. You see that it's essentially greedy heuristics. Meaning that you cannot guarantee you find the best tree, but empirically, it nearly always gives you a good tree. And then variance and extensions, you'll see that following the original ID3 algorithm, you tend to make the tree very large, which takes the risk of overfitting. We'll explain what does overfitting mean. So, why we are going to start with decision trees? The first thing is that it is very simple and intuitive. It is very similar to how human beings classify or predict things. We have in our mind, many psychologists have demonstrated that human thinking and decision procedure is like a tree structure. And decision trees is a tree structure. It's very similar to the thinking pattern of humans, right? And interpretability, right? This is actually is not, I mean, no other models can be better than decision trees in terms of interpretability. Because when I use this tree to make prediction or make decision, you always know why you reach to the decision step, why you give that label, because you see the whole decision procedure, which is a path from the root node to a leaf node. You know the rule, what kind of rules are applied. But nowadays, I mean, many people are fascinated by the deep neural nets, but one major bottleneck of deep neural nets is the interpretability. You don't know why it gives you such kind of classification, right? You don't know why, like Tesla autopilot, why it hits to some white trap, right? You don't know why. You just throw some inputs into some black box, a bunch of neurons. You don't know what's the meaning of those neurons, what's the value of neurons mean, right? So that's the major benefit. It's actually critical for many applications, actually. Consider medical applications, like you want to make some diagnosis, right? You need to explain to other doctors, or you need to explain to your patients that why I give you such a kind of diagnosis, rather than telling, okay, I tell you you got cancer. You don't need to know why. This is actually very critical, and decision trees has very good benefits. And also, don't look down upon decision trees. It's actually very, very widely used, although it is very classical and it was proposed like 30 years ago, or I guess 40 years ago. Yeah. And we'll see that the next topic is about, after decision trees, Bayesian ensemble learning. We see that by combining a set of simple shallow decision trees, you can still get very powerful nonlinear models. And they are very widely used. Okay, so I guess before, we still have 5 minutes, so we can briefly talk about the representation of decision trees. That's at least give a good intuition about definition of decision trees. So what are decision trees? So I'm gonna read through these sentences, which kind of in general, but later we'll see a detailed example. So decision trees is a hierarchical structure that represents data with divide and conquer strategy. You see that it actually divides the data in a recursive way. And each node, from the root node represents the whole data set. Then each node represents a subset of data. And each node is associated with a test feature, meaning that I'm going to use that test feature to further partition the current data set into small subsets. And each small subset will correspond to a new node. a node, say from current node, we look at the test feature and we create a branch for each value that feature can take. For example, suppose currently I have a node here, right, which represents a bunch of data. It's a subset of data, right? Associated with this node is a particular feature, 8. And this feature can take, say, 3 values, right? Say 1, 2, 3, right? And then we just partition this subset of data according to the feature values. So we get subset 1, subset 2, subset 3. The subset 1 means that all the examples in this subset whose feature 8 takes value 1. And all examples in the second subset whose feature 8 takes value 2. And all examples in the third subset, feature 8 takes value 3. That's how they recursively partition the data until they reach a leaf node. The leaf node, what does leaf node? Leaf node means, okay, all the examples in a current subset, they have the same label. They have a unique label. They will stop here. That's how the general decision tree is defined. Right? The leaves of the tree specify the class labels, and so it is also the point to stop growing the tree or partitioning the data. So the general idea of decision tree learning is that given a collection of labeled examples, we want to construct a decision tree to represent, hierarchically, recursively represent this data set. That's it. Okay, so I don't think we have time to go through construction, but I'll give you a representation of decision tree, which we're gonna walk through the construction procedure in the next lecture. And you can see those are colored shapes. This is our training set, right? And by creating procedure, they can be hierarchically represented by this tree. And each node, so you can see this rule node, right? This rule node corresponds to the whole data set. And this rule node corresponds to the subset whose colors are all blue, right? Blue shapes. And here, green shapes. And here, red shapes. And you can further partition according to the type of shapes. You end up with all the leaves, where each leaf corresponds to a subset of the shapes who have the same label. Okay, let's stop here. So on Thursday, we're gonna finish the introduction of decision tree application and start looking at the ID3 algorithm. How do we learn to construct trees from data?